This video is brought to you by Squarespace. Today we're going to look at a really interesting way to construct the Taylor series for the arc sine of x over the square root of 1 minus x squared. We'll actually construct this Taylor series using a differential equation. And then as a bonus, we'll see a nice application of this result. Okay, so let's get going. So I'm going to take this function that we're interested in and call it y, and then cross multiply so I don't have any denominators. So that's going to give me something like this. So we have y times the square root of 1 minus x squared equals the arc sine of x. And now from here, I'm going to take the derivative of both sides. So that shouldn't be a huge surprise given the fact that I said that we would use differential equations along the way. So let's take the derivative of both sides, recalling that we need to use the product rule as well as the chain rule over here on the left-hand side. That'll give us y prime times the square root of 1 minus x squared minus x times y over the square root of 1 minus x squared. So this comes from taking the derivative of the square root of 1 minus x squared. Think about that as a 1/2 power, meaning that it turns into a negative half power using the power rule. And by the chain rule, we've got to multiply by a minus 2x. The 2 obviously gets gobbled up by the half that comes out from the chain rule part. Okay, and then we need to take the derivative of the right-hand side as well, but the derivative of arc sine is well known to be the square root of 1 minus x squared. And now I would say maybe the obvious thing to do would be to clear the denominators. And so let's do just that. Let's take this entire thing and we'll multiply it by the square root of 1 minus x squared and see what happens. So that'll give us 1 minus x squared without the square root times y prime minus x times y equals 1. And now here's our differential equation. Well, maybe together with the fact that y evaluated at 0 is 0, since we know what our starting function is. And now we're going to push this towards a series by setting y equal to the sum as n goes from 1 to infinity of a sub n times xn. Notice I don't have a 0th term here because y of 0 is 0 and the 0th term is in fact equal to the value of the function at 0. Now if we plug this series into our differential equation and find the coefficients of that series, then what we've in essence done is found the Taylor series or the series expansion for our starting function. And that's because the solutions of these differential equations are unique and our starting function by construction satisfied this differential equation. Okay, so now let's maybe take this derivative just to get all of our parts squared away. So the derivative here will be the sum as n goes from 1 to infinity of n times a sub n times x to the n minus 1, like that. And now we'll plug each of these into our differential equation. So the y prime will go there, and then the y will go there. So let's see what that'll leave us with. So we're left with 1 minus x squared times y prime, but that is the sum as n goes from 1 to infinity of n a sub n x to the n minus 1. And then we'll have minus x times y, but that's the sum as n goes from 1 to infinity of a sub n x to the n, and then we have that's equal to 1. But now what I'll do is I'll distribute this first term out, and then I'll multiply this x into the second term. So let's see, the 1 multiplied onto this sum will just give us the sum. So I'll copy that down. The sum as n goes from 1 to infinity of n times a sub n times x to the n minus 1. And then we'll have minus the sum as n goes from 1 to infinity of n times a sub n times x to the n plus 1. So now that's n plus 1 because we multiplied by x squared. And then likewise, moving this x in here gives us the sum as n goes from 1 to infinity of a sub n x to the n plus 1. And then we have 1 left over on the right-hand side. There's not really much going on there. Okay, so now let's move to the top over here and see where we go. Before we copy that up there, I'd like to maybe pull out the first two terms from this first sum. And that's just because notice this starts with a constant term, whereas these two start with an x squared term. So that means they'll start with the same level of, power of x. So let's see, the n equals 1 term will give us a sub 1. So here we have this is a sub 1 plus the n equals 2 term will give us 2a sub 2 times x, because we've got 2 minus 1 is 1, and then we'll start at n equals 3. So that'll be the sum as n goes from 3 up to infinity of exactly the same thing. So we have n a sub n x to the n minus 1. And then we'll subtract these two, but notice that these are indexed the same way, so I can combine them quite easily. So that'll end up being something like this, minus the sum as n goes from 1 to infinity of n plus 1 times an times x to the n plus 1. We have all of that is equal to 1. Okay, so now we're getting kind of scrunched over there, so let's maybe start with the clean board and an equation that
Before we continue, I'd like to thank today's sponsor, Squarespace. Squarespace is a service that takes the hassle out of creating a website. You don't have to be a programmer to have a beautiful, responsive, and feature-rich website. Because of their support, we are able to do what we love. With Squarespace, you too can focus on what you love and leave the technical stuff to them. With simple drag and drop actions, access to the code if you need it, and domain services that help you get your site online quickly. I use Squarespace for my own website and I find it easy to use with plenty of integrations. They even have a plugin for LaTeX. It allows me to include equations on my website very easily. Whether you need a place to sell your wares or to show your art, Squarespace has the tools that you need to keep your website modern and easy to use. Give Squarespace a try by going to squarespace.com/michaelpenn to save 10% off your first purchase of a website or a domain using code michaelpenn. Thanks again to Squarespace for sponsoring today's video that we are now returning to.
Okay, so this is where we ended up. Now, before starting our next round of reindexing and such, I'd like to notice that everything except for this a1 term on the left-hand side contains a power of x. Whereas there's only one thing on the right-hand side, and that is a constant. And so these constant terms must be equal. Now, you could also maybe plug x equals 0 into this whole thing, and you'll see that everything cancels except for the two red underlined things. But let's maybe collect that over here. So let's notice we know that a sub 1 is in fact equal to 1. We also know that a sub 0 is equal to 0 from our previous discussion. So that's good. We know the first two coefficients of this power series. Now let's do a little bit more work. Let's maybe do a change of index in this sum right here to put it in line with this sum right here. So I think our best bet is to take every value of n and replace it with n plus 2. Let's see what that'll do. That'll change this n here to an n plus 2. So this index here will become n plus 2, and then this exponent here will become n plus 2 minus 1 or n plus 1. Furthermore, our starting bound of summation is now 1, because when n plus 2 is equal to 3, n is equal to 1. But using this, we can combine these two sums because they're like indexed correctly so that the powers of x are the same. So let's see where that leaves us. So maybe canceling the a sub 1 from both sides, because we know that a sub 1 is equal to 1, that'll leave us with 2a sub 2x, and then plus the sum as n goes from 1 up to infinity of, let's see, n plus 2 times a n plus 2, that's this bit right here, and then minus n plus 1 times a n, that's this bit right here, and this is all multiplied into x to the n plus 1. Now that's all equal to 0 over there on the right hand side because we did that cancellation. But now let's like zoom in on this thing a little bit and notice if we were to expand it, it would be some coefficient, which I'm actually not going to worry about at the moment, times x squared plus some coefficient times x cubed, dot, dot, dot. The important thing is it starts at x squared. Notice that the right-hand side has no x squared terms, and this thing that I've underlined in green has no x terms. That means the only x to the first power term is this term right here, which means, in fact, a2 must be 0. So, you know, all of that discussion that we just had means that we know another value of our coefficients. We know, in fact, a2 is equal to 0. Okay, so that means I can delete this from the game as well. So that's equal to 0. Okay, but now I've got this power series is identically equal to 0. That means each of its coefficients must be equal to 0. But the coefficients here are not quite as simple as the other ones I've seen. The coefficients are these things that I'm underlining in yellow. So that gives us an equation on the coefficients. So for instance, we know n plus 2 times a n plus 2 minus n plus 1 times a n must be equal to 0. And this is for all n bigger than or equal to 0. Now we can solve for a n plus 2 in terms of a n. So we have a n plus 2 is equal to, well, let's write it down. This is going to be n plus 1 over n plus 2 times a n. But let's notice that a0 and a2 are both 0. But using this, we'll see that a4 is a multiple of a2. a6 is a multiple of a4. That means all of the even terms are multiples of a2, which we've decided is 0 over there. So putting all of that together, we see that in fact a sub even is equal to 0. Or maybe a sub 2n if you want to write it more properly, but I think this kind of offhand description is kind of nice. But if we know that a sub even is equal to 0, well, now we've got to figure out a sub odd. Notice a sub 3 will be a multiple of a sub 1, which is 1, so that's definitely not going to be equal to 0. Well, let's see what we get here. So we'll have a sub 2n plus 1 is in fact going to be equal to 2n over 2n plus 1 times a 2n minus 1. So that's how the 2n plus first term depends on the 2n minus first term. Okay, well, let's take that down one step. And that means we'll have 2n times 2n minus 2 over 2n plus 1 times 2n minus 1 times a 2n minus 3. Just applying the recursion one more time. And then we can take this all the way down to the ground and we'll get 2n times 2n minus 2 times 2n minus 4 all the way down 4 times 2 over 2n plus 1 times 2n minus 1 all the way down to 5 times 3 times 1 times a sub 1, which is 1. So that's our maybe closed form for a sub 2n plus 1. That being said, there is a nice way to write that down with this double factorial notation. So in fact, a sub 2n plus 1 is 2n double factorial. So a double factorial means you skip or you descend by 2 at each step of the product over 2n plus 1 double factorial. So that's our closed form here. Our odd terms have that form and our even terms are 0. So that means, well, we've done it. We found a Taylor expansion for this function. Now let's look at a quick application. Okay, so this is where we ended up. The arc sine of x over the square root of 1 minus x squared was equal to the following power series. Now let's see our nice application here. So let's look at the arc sine of x quantity squared. And let's notice that that's exactly equal to twice times the integral from 0 to x of the arc sine of t over 1 minus the square root of 1 minus t squared. And that's just by a simple u substitution. Okay, but now this is going to be the same thing as 2 times the antiderivative of this sum right here. But the antiderivative of this sum right here will still be a sum as n goes from 0 to infinity. And then we'll have 2n double factorial over 2n plus 1 double factorial. But now we need to multiply by a 2n plus 2 in the denominator because we're raising our exponent from 2n plus 1 to 2n plus 2. So we've got something like that. Okay, but now I want to do a bit of simplification. Let's take this 2 right here and have it cancel this 2n plus 2 down to an n plus 1. And now we're going to do a sneaky evaluation of both sides that'll bring us towards a nice identity. So maybe over here on the left-hand side, we'll set x equal to 1/2, which means, of course, since we have equality, we want to do the same thing on the right-hand side. So like I said, we're going to take x to be equal to 1/2. But we're also going to do an index change over there on the right-hand side just to make everything look a little bit nicer. And what I'll do as well is take all of the n's and replace them with n minus 1s. And that'll mean that our sum starts at n equals 1 instead of n equals 0. Okay, so let's see what that leaves us with. So the arc sine of 1/2, well, that's where sine is equal to 1/2, which is pi over 6, but we're squaring it, so that's pi squared over 6 squared, which is 36. And now I'm going to write what we have over here, so it's going to sneak way over here. And I'm going to write it just as is first, after this evaluation at 1/2 and this n going to n minus 1. And then we're going to cleverly rewrite it so that it simplifies nicely. So here I have the sum as n goes from 1 to infinity. The index change means we start at 1. And then we have 2n minus 2 double factorial because of the index change over 2 to the 2n times 2n minus 1 double factorial because of that index change, and then times n. So this n comes from this n plus 1 after the index change, and then I've got 2 to the 2n instead of 2 to the 2n plus 2 for that same index change reason. And now we're going to start some simplification on this thing, and it'll just be a lot of clever rewriting. So the first thing that I'll do is I'll bring a 1/2 out front. And we'll see why I need to bring a 1/2 out front. It'll make everything kind of balance correctly. Then I have the sum as n goes from 1 to infinity. Now I'm going to take this 2n minus 2 and I'm going to rewrite it as what the double factorial means. So that's 2n minus 2 times 2n minus 4 all the way down to 4 times 2. Okay, nice. Then I'm going to do the following. Notice that after taking this 1/2 out, I have 2 to the power 2n minus 1. So I'm going to take n minus 1 of those and put them under each of these. So here I've got 2 times 2 all the way down to 2 times 2. Okay, so let's see where we are. This is n minus 1 2's, 1 2, so I've used n 2's. That means I have n 2's left over. Okay, so now I'm going to continue this process. I'm going to take this n right here and I'll move it to the left-hand side of this second denominator, and I'm going to combine it with one of the 2's. So 2n. And that's going to leave me with n 2's left over. I'll write that as 2 to the n over here. Okay. And then let's notice I've got this 2n minus 1 double factorial to fill in right here. So I'll write this 2n minus 1. The next one would be 2n minus 3 all the way down to 3 times 1. Okay, and now I'm going to multiply by a special version of 1. And that will be to complete this double factorial into a factorial. So here I'll multiply by 2n minus 2. And then here in between those two, I'll multiply by 2n minus 4. But that means I need to multiply in the numerator as well. 2n minus 2, 2n minus 4. And that's going to descend all the way down. There I'll multiply by 4. There I'll multiply by 2. To the left of 3, really between 3 and 5. and between 3 and 1. So that goes all the way down here to, like I said, 4 times 2. Oh, and I just realized this should be 2 to the power n minus 1. Just count up the number of 2's we've used. We used n minus 1 of them here, n minus 1 of them here, 1 of them here, 1 of them here. That's 2n of them. Okay, and now we've used all of our parts and we can get to some simplification. So notice that this 2 will cancel this down to, let's see what it is n minus 1. Then this 2 will cancel this down to n minus 2. And I think you can see where we're going. This 2 cancels this 4 down to 2. This 2 cancels this 2 down to 1. Okay, that's nice. And then very, very similarly, this 2 to the n minus 1 will cancel this product the same way. So that'll cancel this down to what is essentially n minus 1 factorial, because that's what we're left with over here on the left-hand side. Okay, so let's see what we have when all is said and done. We have 1/2. And then we have the sum as n goes from 1 to infinity. I'm left with n minus 1 factorial times n minus 1 factorial in the numerator. And then in the denominator, all I'm left with is this 2n, 2n minus 1, 2n minus 2, 2n minus 3, 2n minus 4, all the way down to 1. That is 2n factorial. But this isn't quite everything we need. I'll also do one more like simplification here, and I'll multiply the numerator and the denominator by n squared. So that'll change the numerator into n factorial times n factorial. Okay, but now the most important thing to notice here is that we have a reciprocal of a central binomial coefficient. So the binomial coefficient 2n choose n is in fact 2n factorial over n factorial times n factorial, just by the definition of a binomial coefficient. So putting that little observation in play here, we'll see that we have in fact 1/2 and then the sum as n goes from 1 up to infinity of 1 over 2n choose n times n squared. But now let's clean that up a bit. Let's maybe multiply both sides by 6 and collect what we have over here. So we have the sum as n goes from 1 to infinity of 3 over 2n choose n times n squared is equal to pi squared over 6. So like I said, that's from multiplying both sides of this by 6. Now, why would we do that? Because this pi squared over 6 is exactly the value of the zeta function evaluated at 2. In other words, the sum as n goes from 1 to infinity of 1 over n squared. So we've got this nice relationship between these two similar looking sums. And that being said, we will have an upcoming video where we use this application of this closed form together with like an infinite product of matrices. So maybe be on the lookout for that, and that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.